Welcome to ChemE-Shiksha. Today we'll be starting another topic of pump, that is priming, cavitation and NPSH. These three topics are the most important topics in the pump lecture series from your interview perspective. So let's start today's video. So first of all, priming. So we know that the pressure developed by the pump is delta P is equals to rho into G into H. So if the rho, the density of the fluid inside the pump, if it is very less, then the pressure developed by the pump delta P will be also very less, because delta P is equals to rho into G into H. So if rho is very less, that means the fluid density that has to be pumped by the pump, that will be, if that is very less, then the pressure developed by the pump will be also very less. So at the starting of the pump, where if the pump is full of air, as the air density is very less, so that's why the pressure developed by the pump will be very less, because the pump has to develop the within the pump there is air, so air density is very less. That's why rho of air is very less, so delta P, that is pressure developed by the pump, will be also very less. Now at that point of time, if the pressure in the pipeline is more than that, then the air will not be pumped out by the pump and there will not be any vacuum created. So that's why the pump will not be able to suck the fluid from the sump. So that's why the priming is required. Priming is actually the process of filling the pump and suction pipe with the liquid. So if the liquid that is the pump is already previously it is filled with some liquid, then the pressure developed by the pump will be higher, because the rho of the fluid will be always higher than the rho of air, because air density is very less. So if the pump is not filled beforehand, then the pump will not be able to suck the fluid from the sump. So that's why priming is done, where the pump is first filled with the fluid or the liquid and then it is started. If then it is started, then it can develop sufficient amount of pressure so that it can be pumped out and vacuum will be created inside the pump, and the pump will be able to suck the fluid from the sump to the eye of the impeller. Nowadays there are self-priming pump, which actually includes the non-return valves in the suction line, which will not allow the fluid inside the pump to drop, and it will retain the fluid inside the pump. So in the next time when the pump will be started, then the pump will create a sufficient pressure across that, and it can pump out the fluid, and it can and create a vacuum within the pump. So the fluid which is in the sump, it can be easily sucked by the pump and the pumping procedure can be easily done. So that is the significance of priming. So always ensure that priming is done. So the self-priming pumps use a one-way valve that I already told you. One non-return valve is used in case of self-priming pump. So these are the non-return valve, means it will not uh, allow the liquid or the fluid to return to the sump at the end of the process. So it will retain the fluid inside the pump, and that's why when the pump will be started, so it can build a sufficient pressure and create suction at the eye of the impeller. Now the next phenomena is the cavitation. So before moving towards the cavitation, we have to understand this graph. So we know the pressure, this is the pressure versus temperature curve. This is the vapor pressure curve. So we know that at a constant pressure, if we keep the pressure constant, then if we increase the temperature, so we will move from this liquid region to the vapor region. And similarly, if we at keep the temperature constant, and from this constant temperature, if we increase the pressure, then we will move from this vapor region to the liquid region, and if we decrease the pressure, we will move from this liquid region to the vapor region. So that is the thing, that is at constant temperature, if pressure is decreased, then liquid will convert into vapor, and if pressure is increased at constant temperature, then vapor will be again, it will condense and it will form liquid. So it is written over here that at constant pressure, increasing temperature causes liquid to vaporize, and at constant temperature, decreasing pressure also leads to vaporization. We know vapor pressure is the pressure at which the liquid and vapor coexist. So inside the pump, the if at any point the local pressure is falling below the fluid vapor pressure, then there will be some problem. That is, at the if at any point the pressure goes below the vapor pressure of the fluid, then the liquid will start forming vapor, because we know that at constant temperature, if pressure decreases, then liquid will start converting into vapor. So as the vapor as the pressure inside the uh, pump goes below the vapor pressure of the fluid, so it will start forming vapor bubbles, and from the suction to the eye of the impeller pressure, we know pressure is actually decreasing. So from this curve we can see that from the suction point to the eye of the impeller, this is the eye of the impeller, so the pressure actually decreases, and at any point if this pressure goes below the vapor pressure, then the liquid inside the pump will start forming vapor bubbles, and again at the point of the eye of the impeller, the pressure is actually minimum. So from this eye of the impeller, as to the discharge point, pressure again increases. Now as the pressure increases from this eye of the impeller to the discharge point, so these vapor bubbles will start collapsing. So we know that when liquid is converted into vapor bubbles, it will the volume is increases by many times. Now again from when the pressure increases, and vapor bubbles will collapse, and it will form liquid, then it will create a vacuum, because as the vapor bubbles are the volume of the vapor bubbles is increased by many times, so that's why when these vapor bubbles will collapse, then it will create vacuum inside at that point. So to ensure there is no vacuum, the surrounding liquid will move at a high velocity at that point, and it will hit the metal surface of the pump. So this will erode the pump surface. So this phenomena is actually called the cavitation, that is the formation and collapse of vapor bubbles inside the pump is known as cavitation. So how this is happening now, when we know that from the suction point to the eye of the impeller, pressure is actually decreases. So when this local pressure, that means pressure at any point, it goes below the fluid vapor pressure, then the liquid will uh, convert into vapor bubbles, and as the pressure again decreases, then the vapor bubbles will grow. But after the eye of the impeller, where the pressure is minimum, so after that minimum point, that is eye of the impeller, pressure again increases, then the vapor bubbles will start collapses violently, and it will uh, cause noise and damage, because when the vapor bubbles will collapse, then vacuum will be created, and to ensure there is no vacuum, the surrounding liquid will move, and it will hit the surface of the pump, metal surface of the pump, and it will create some noise, and it will damage the pump component. So this phenomenon is very common at the eye of the impeller, because at the eye of the impeller the pressure is the minimum. So if it is below the vapor pressure of the fluid, then this cavitation occurs. So the effect and dangers of cavitation. So as I told you, the collapsing bubbles as pressure increases. So the liquid will hit the surface of the pump with very high velocity and force. So as the vapor bubbles will start collapsing, so the liquid from the surrounding, it will come with very high velocity and hit the surface of the pump. So it will create noise and vibration, and it will also erode the pump surface and reduce the efficiency of the pump, and this will result in low suction pressure and fluctuating amperage. So as the vapor bubbles occupy the most of the area, so the liquid flow becomes erratically low, and the pressure also becomes erratically low. The suction pressure and amperage also becomes low. So these are the effects and dangers of cavitation. So to ensure that there is no cavitation, there is one point, that is the NPSH, or the net positive suction head. So NPSH helps to determine if cavitation will occur or not. There are two types of net positive suction head. One is NPSH available, another one is NPSH required. So if NPSH available is more than the NPSH required, then that is a safe operation. That means there will not be any cavitation. Now NPSH available is calculated from the suction condition. So NPSH available is equals to Pi by rho g plus Vi square by 2g. So Pi and Vi, these are the suction condition. Pi is the suction pressure, Vi is the velocity at the suction point, minus Pv by rho g. So Pv is the vapor pressure of the fluid. So this is the NPSH available, which is calculated from the suction condition, and the NPSH required, it is given by the pump manufacturer. So if liquid pressure inside the any position of the pump is not less than the vapor pressure, then cavitation will not occur. Now we need to quantify how much liquid pressure is far from the vapor pressure. So if the suction pressure minus vapor pressure is less than 0, that means suction pressure is less than vapor pressure, so that means cavitation will occur for sure, because at suction only your pressure is less than the vapor pressure. Now from the suction the pressure will again drop, so it will go again below the vapor pressure, because it is already below the vapor pressure. So it is obvious that cavitation will occur. But if Ps minus Pv is greater than 0, that means suction pressure is greater than the vapor pressure, so then you cannot say that whether cavitation will occur or not. As pressure at the eye of the impeller is less than the suction pressure, so we cannot tell that whether the pressure at the eye of the impeller is less than vapor pressure or not. So if we can measure the pressure at the eye of the impeller, and if it is more than the vapor pressure, then we can certainly tell that there will not be any cavitation, because we know the pressure is minimum at the eye of the impeller. So if that minimum pressure is already more than the vapor pressure, then there will not be any problem of cavitation. But the problem is the pressure at the eye of the impeller is not measurable. So we can only measure the pressure at the suction point, that is the suction pressure Ps. But one thing we can the manufacturer can provide us, that is from the suction point to the eye of the impeller, what will be the pressure loss. So the pressure loss, that is a PL, the pressure loss from the suction point to the eye of the impeller. So if Ps minus Pv is greater than PL, or from in the head term, if we write that Ps minus Pv by rho g is greater than PL by rho g, then for sure we can tell there will not be any problem of cavitation. So that means the NPSH available is greater than the NPSH required. So If NPSH available is greater than NPSH required, then it will prevent cavitation. That means cavitation will not occur. Now the point of troubleshooting. That means how to troubleshoot. That means how to ensure there is no cavitation. So we know that to ensure there is no cavitation, NPSH available should be more than the NPSH required. So by somehow we have to increase the NPSH available. So there are certain points to increase the NPSH available, like increase the suction pipe diameter. So if we increase the suction pipe diameter, that means suction pipe diameter is increased, means suction pipe area is increased. So that means the velocity is reduced, because we know that area into velocity is constant from the equation of continuity, that A into V equals to constant. So area into velocity is constant. So as the suction pipe diameter is increased, so that means suction pipe area is increased. That means at the suction the velocity is decreased. So as velocity is decreased, so the head loss, frictional head loss is decreased, because we know that HFS is proportional to V square. So at the suction the frictional head loss is decreased. That means the head is more, that is NPSH available is more. So by increasing the suction pipe diameter, we can increase the NPSH available. Another thing is by lowering the working fluid temperature, which will lower the vapor pressure along with it. So we know that the local pressure at any point should not be less than the vapor pressure. So to ensure that, we can decrease the vapor pressure by decreasing the fluid temperature. Another thing is increasing the liquid level H above pump. So NPSH available, we have to increase the NPSH available. So NPSH available is directly proportional to the liquid level inside the pump H. So if we increase this liquid level above the pump, that is H, then the NPSH available will be increased. So that's why by increasing the liquid level, we can increase the NPSH available, which will make, which can make sure that cavitation is not occurring. Another point is decrease the discharge flow to reduce the suction flow losses. So if we decrease the discharge flow, automatically the suction flow is decreased. So if suction flow is decreased, that means at suction, from the similar logic, that if suction flow is decreased, that means the velocity of the suction is decreased. That means the HFS, the flow losses, the head loss, frictional head loss at the suction is decreased. That means at suction your head is increased, that is NPSH available is increased. And the last, operate the pump at a lower RPM, thus flow rate. So if we operate the pump at a lower flow rate or lower RPM, then also we can increase the NPSH available. So in this way we can by increasing the NPSH available, we can ensure that NPSH available is always greater than NPSH required, and there is no cavitation. So this is all about this video. If you like this video, please hit the like button and subscribe my channel. Share this video with all of your friends. Be a part of a growing network of future ready chemical engineers. Join this community. Thank you for watching this video.